5 symbols are waiting in the dark: E, I, pi, 1, and 0. Written together, they make a sentence that seems impossible. A number associated with growth is raised to an imaginary power, meets pi, adds 1, and becomes nothing. We will not ask you to admire that sentence. We will make it move. Watch the amber point. It begins at 1, leaves home, travels through a world we have not built yet, and returns opposite its starting place. Then one final step restores 0. In 12 minutes, every part of that journey will be constructed from operations you can see. No symbol gets a free entrance. The question is simple: how can repeated growth produce a perfect turn? Begin with a road. 0 is our origin, the place from which distance is measured. 1 means 1 step to the right. 2 means take that step twice. 3 means take it 3 times. They are addresses created by repeated motion. To reach -1, walk the same distance in the opposite direction. That gives us a useful symmetry. 1 and -1 are equally far from 0, but face opposite ways. Addition now has a visible job. Adding 1 shifts the traveler 1 unit right. Adding -1 shifts it 1 unit left. Subtraction reverses a shift. These rules are not pictures pasted onto arithmetic. The picture preserves the arithmetic exactly. Keep one fact in memory. The amber point at 1 is our starting state and 0 is home. The rest of the film will change the meaning of movement without changing that identity. Addition moves a point. Multiplication can move an entire world. Multiply every address by 2 and every point doubles its distance from 0. Multiply by 1/2 and the road contracts. Now multiply by -1. Every point keeps its distance and crosses to the opposite side. 1 becomes a -1. -1 becomes 1. Watch what the whole transformation does. It makes a half turn around 0. Do it twice and the road returns. Algebra records that return as -1 times -1 equals +1. The invariant is distance from 0. The change quantity is direction. This is our first clue that multiplication can encode geometry. A factor need not merely make a quantity larger or smaller, it can tell a state which way to face. But a half turn leaves a difficult question. What multiplication would make only half of that half turn? Every positive number squared is positive, and negatives squared are positive. Nothing on the line can square to -1. The obstruction belongs to the road, not to logic. Give the road a second direction. Horizontal positions remain ordinary real numbers. Vertical positions record multiples of a new unit called I. Define multiplication by I as a quarter turn counterclockwise. 1 turn carries 1 to I. A second quarter turn carries I to -1. So I times I equals -1, exactly as required. A third turn reaches -I and a fourth returns to 1. We enlarge the map so the missing operation has somewhere to go. The amber traveler can now rotate, but we still have no reason for E, the growth number, to control that rotation. That bridge is the hard part, and we will build it rather than announce it. Imagine 1 unit of value growing by 100%. Applied once, 1 becomes 2. Split the growth into 2 equal updates. Each update multiplies by 1 plus 1/2, so the result is 1.5 squared, 2.25. 4 updates give 1 plus 1/4, multiplied 4 times, about 2.44. Earlier fractions keep growing through later updates. Continue with 832, then hundreds of smaller updates. The results settle toward a number, 2.71828, called E. The decimal is not the definition. The process is. With n updates, the factor is 1 plus 1 over n, repeated n times. As n grows without bound, that expression approaches E. Replace the total growth of 1 with any amount x. Repeating 1 plus x over n times, approaches e to the x. An exponent is an accumulated instruction. Many tiny proportional changes compressed into one symbol. Instead of adding each tiny update in the forward direction, add it perpendicular to the direction. Perpendicular means multiply that small change by I. Suppose the desired turn is an angle theta. Divide it into n pieces. 1 microstep multiplies the current position by 1 plus I theta over n. Repeat the same local rule n times. With one enormous step, the traveler misses the circle badly. With 2 steps, the route is a coarse corner. 4 steps make a recognizable bend. 8 and 32 steps wrap closer to the unit circle. Nothing in the rule says circle. Each step knows only the current direction and a tiny sideways change, yet the accumulated path turns. This is the same structure that produced E1 plus a total change divided into n parts, repeated n times. The only difference is that the change points through I. If the limit exists, the repeated product is e to the I theta, but resemblance is not proof. The finite polygons drift slightly outward, and we must account for both their length and their angle before we trust the circle. Magnify 1 microstep. Before the step, the radial component has length 1. The added perpendicular component has length theta over n. Together they form a right triangle. By the Pythagorean theorem, the new length factor is the square root of 1 plus theta squared over n squared. The turning angle of that triangle is arctangent of theta over n. Repeat the factor n times. The total radius is the square root of 1 plus theta squared over n squared raised to the n. The total angle is n times arctangent of theta over n. The unwanted radial excess in each tiny step is second order. It depends on 1 over n squared. There are n steps, so the accumulated scale of that error behaves like n over n squared, which is 1 over n and vanishes. For the angle, a small arctangent is almost equal to its input. Each piece approaches theta over n. N pieces approach theta. Thus, ever smaller sideways updates preserve unit distance while accumulating the requested turn. The polygon is not declared to be a circle. Its measurable errors are driven to 0. That limit is the exact bridge from repeated exponential change to rotation. Return to the full observatory. The traveler now stays 1 unit from 0 while its angle changes. Any point on this unit circle can be described by 2 shadows. Drop a vertical guide to the horizontal axis. That coordinate is called cosine of theta. Project across to the vertical axis. That coordinate is called sine of theta. Because vertical distance is measured in the I direction, the point itself is horizontal coordinate plus I times vertical coordinate. Cosine theta plus I sine theta. But our microstep experiment reached the same point by the limiting product that defines e to the I theta. One endpoint has 2 faithful descriptions, therefore e to the I theta equals cosine theta plus I sine theta. This is Euler's formula, but notice when the name arrives. After the operation, the measurements and the limit, it is not a spell connecting unrelated celebrities. It says that infinitely refined proportional change, aimed sideways, traces the same geometry that sine and cosine measure. Watch 1 revolution. The amber point moves steadily, while its 2 projections breathe between -1 and 1. A circle, 2 waves, and 1 complex exponential are 3 observer views of the same motion. Take a circle and compare its distance around with its distance across. For every circle, circumference divided by diameter has the same value, called pi. For a unit circle, the radius is 1, the diameter is 2, so the full circumference is 2 pi. Angles can now be measured. Lay an arc along the circle and divide its length by the radius. That ratio is the angle in radians. On a unit circle, angle and arc length have the same numerical value. A full turn covers arc length 2 pi, so a half turn covers pi. It is not there because the equation wanted a famous constant. It is the travel instruction for reaching the opposite side of a unit circle. Set theta equal to pi. The exponential journey begins at 1 and makes 1/2 turn. The traveler must arrive at -1. We can now return to the opening sentence and read it line by line. E2, the I theta equals cosine theta plus I sine theta. Choose theta equal to pi because pi radians is a half turn. At a half turn, cosine pi equals -1. Sine pi equals 0. Substitute those coordinates. E to the I pi equals -1 plus I times 0. The vertical term disappears, leaving e to the I pi equals -1. Perform the balancing move, add 1 to both sides. E to the I pi plus 1 faces -1 plus 1, which returns to 0. So e to the I pi plus 1 equals 0. Every mark has a job. E compresses repeated tiny change. I turns that change sideways. Pi requests a half turn. The first one is the starting point. and the added one balances its opposite. 0 is the origin. The beauty is not that 5 famous symbols share a line. The beauty is that 5 operations close one journey without residue. The deeper insight is the engine. Keep the exponential rule and change the direction of its tiny updates. Aim them forward and distance grows or decays. Aim them perpendicular and direction turns while distance stays fixed. Combine a forward component with a sideways component and the traveler follows a spiral. Scale and rotation accumulate together. The exponent is not merely a superscript telling us how many copies to multiply. It can encode a continuous generator, an instruction repeated. That is why complex exponentials appear wherever systems oscillate. Waves, alternating currents, vibrations, control systems, signal phases, and rotations. The mathematics does not claim those things are literally wheels. It gives observers a language for change that repeats and turns. In the observatory, the same event can be watched as a path, 2 projections, a changing phase, or an equation. Each view hides something and reveals something. The discipline is to preserve the same underlying state across them. Euler's formula succeeds because the identity survives every gateway. Local, microstep, polygon, circle, coordinates, and symbol. We can finally look at the opening line. E is accumulated proportional change. I rotates each tiny change through a quarter turn. Pi asks for exactly half a revolution. The traveler that began at 1 arrives at -1. Adding 1 brings the total home to 0. The equation is short because the journey has been compressed. Its deepest lesson is a change of viewpoint. Growth and rotation are not strangers, they are 2 directions available to the same repeated operation. Numbers can be places and motions, and a good equation is not a cabinet of beautiful symbols. It is an observatory window, views of one event, aligned so perfectly that the traveler returns where the story promised.